Start recording. Good morning, everybody. Okay, so we were at the end of the chapter about heat. Still have what, 2 weeks of teaching, so it's fine. Um, what we were saying last time, as you may remember, well, I hope you remember something, is that when we are going through a change of state, okay, then we need to take that into account in our calculations of the heat which is needed, okay. So if I do this general diagram, okay, this diagram shows uh, a state change from here where you have, for instance, a solid uh, to here where you have, for instance, a liquid, okay. And if you have a situation like that, you have three different phases. This is temperature as a function of time. You have three different phases. This is one phase in which you are heating up the material. So it's the normal formula MC delta T. For the Q3, it's also the normal formula MC delta T, but be careful because here you have a solid, so it's going to be the specific heat of the solid, and here you have a liquid, it's the specific heat of the liquid, which are generally different. And for the second phase, this phase in which you are changing from a solid to a liquid, this phase is given, the energy necessary for this phase is given by the mass times uh, times this LF, okay, which we call the latent heat. LF is the latent heat. And the latent heat is the quantity of heat that is necessary to change the state for 1 kilo of the substance. So this is in joule per kilogram. Okay, this is why we multiply just with the mass. Here we don't have a delta T factor. Why? You understand why we don't have a delta T factor? Have an idea? In this second phase? Hmm? Yeah, exactly. The temperature here doesn't change, okay? And be careful, this temperature is the fusion temperature for water. Yes, it's 0 degrees, but for any other substance, it's going to be another value of the temperature here, okay? So I gave you two exercises to do for today, which were exercises 1 and 2. So let's do that together. Let me just erase this, which I wrote here, which is taking space. Okay. Okay, the first exercise is quite easy. Does somebody want to do the correction? No? No voluntaries. It's too early, huh? You are sleeping at that time. I know you guys. Okay. You want to melt completely. Did we do that one or not? No, we don't. We didn't do it, right? Hello? Did we do? You don't know. Okay. So let's do it. Okay, you want to melt completely 50 grams of lead, and the lead is initially at 20 degrees. Okay, so let's do a small diagram. I find it useful to do a small diagram for this kind of cases. You start with lead at 20 degrees. Okay, so lead at 20 degrees is solid, as you probably know. And then we need to know until which temperature we must heat the lead so that it starts melting. Okay, so there is this plateau here which corresponds to melting of the lead. At the beginning of the plateau, we have a piece of lead which is solid. At the end of the plateau, our lead will be uh, in the liquid phase. It has undergone fusion. Okay, so we have two phases. We have one phase here. We have a second phase here. Okay, the first phase is a normal phase, is a normal heating phase. Okay, so the Q1 is going to be M times C lead solid times the delta T, but the delta T, how should we write it? If I want to write the detail of the delta T, okay, the final temperature, we don't know it because we don't know yet fusion temperature of the lead, so this we have to look for in the table, and then minus the initial temperature of the lead, which is 20 degrees. Okay, here the lead, you need to warm it up until the fusion temperature, and this we need to see in the table. And then the quantity Q2 for the second phase, for the melting phase, is just given by M times the latent heat of fusion of the lead. Okay, and this is also something we need to look for in the table, right? So let's take the CRM table and see where these guys are. So independently of the addition you have, it's all in these pages which look like that. Okay, so I don't know on which page you have them. I have that on page 162 and following ones, but I don't have the latest edition. And in these tables, I recall you that you have 4 pages for each of these substances. So here you see you have hydrogen until zirconium, and then again hydrogen until zirconium with other properties. Okay? And this is the page which is interesting for us. Can you read? Can you see? Because here we have the fusion temperature and the boiling temperature. Okay, what we need is the fusion temperature. So for the lead, it's here. It's 327.5. This is the fusion temperature of the lead, the temperature at which it melts. Okay, so let's put this in here. Okay, let's put in the numbers. We have the mass, which is 50 grams. So how should I write it? 50 grams, I should write it in kilograms. So 0.05. And then the specific heat of the lead, this we didn't look for. So specific heat in French is chaleur massique, and you see that you have different values for the solid, for the liquid, and sometimes you have the value for the gas. In the case of lead, okay, you have it here. It's 0.129 times 10 to the power 3, so it's 129 or 130. I think we took 130 until now, because the table you have in this course gives you 130. And then we have our fusion temperature, 327.5 minus 20, okay? And that is going to give us a result which we are going to compute in a minute. Now, the second value we need is the mass, again 0.05, times the latent heat. And you see you have the latent heat of fusion here, and you have the latent heat of vaporization. So the latent heat of fusion is for when you want to go from a solid to a liquid, and the latent heat of vaporization is when you go from a liquid to a gas. Okay, so we are going to take the fusion one, and you have the value for the lead down here. It's 0.25 times 10 to the 5. Therefore, it's 25 times 10 to the 3. check the units, it's joules per kilogram. Okay, 25 times 10 to the 3, 25,000. I can write it here, 25,000. Okay, so now we can compute these two guys. I don't have much space. Let me try to optimize that a bit. Okay, let me do it like this. And now let me take my calculator. Are you still there? Hmm? Hello, class. Are you alive? Yes, good. It's like like yeah, it's like in class at this hour in the morning you are still sleeping. So 0.05 times 130 times 327.5 minus 20. That gives us a nice 1998.75 joules. It's not much, okay? 1998. You remember, usually we were ending up with huge numbers. This is just due to the fact that, first of all, the C of the lead is very small, and then the quantity of lead is very small too, okay? And for the second one, we have 0.05 times 25,000, and that gives us 1,250 joules, okay? So we have these two values, so that now the total heat that we need is, of course, the sum of Q1 and Q2, okay? So it's this guy plus this guy, and so this plus 1,998.75, that's now 3,248.75 joules for the whole process. Okay? Ça va? Allô, allô? Allô, la Terre? Hey, good. Questions about that? One heating phase, one transformation phase, one term for each, different types of term, you do the sum and voila. It's not complicated. Okay? Okay. Let's do the next one. Did somebody do the next one? You need to think a bit more for the next one. Okay, it's not as straightforward. Let me do a bit of order on my desk. Okay, so this exercise, I'm going to do it, I'm sorry, going to do it on a separate piece of paper because here I don't have space. Okay, take the, well, there is some space on the back, but I want to do it on a separate page. So we have 1 kilo of water, okay? We have 1 kilo of water. This water is at 10 degrees Celsius, and 1 kilo of ice, and 1 kilo of ice, so water in another phase, at a temperature of minus 10 degrees, okay? And now we need to find the equilibrium temperature. That will be pretty easy to find. And how much water and how much ice will we have at equilibrium? Okay. So how can we solve that? What do you think? Let me put that straight. What do you think we can do here? You have an idea? Are you going to say something, or should I do the speaking as usual? Okay. We did this small diagram. Now I would like to redo the same diagram, but to compute a few numbers. Okay, I would like to compute a few numbers. We have ice at minus 10 degrees. Okay, and then this ice is going to warm up until 0 degrees. Okay, it's clear that if we take water and ice together, the ice is going to melt and the water is going to become cooler. Okay, So the water is initially at 10 degrees. Okay? So we have one substance which is here in the diagram and another substance which is here in the diagram. This is our ice and this is our water. Okay? Let's see how much energy it takes for the ice to warm up to 0 degrees, and let's see also how much energy how much energy the water releases when it goes down in temperature to 0. Okay, and then we are going to see where in this plateau we are. But what's going to happen probably, we're going to check it with numbers, but what's going to happen probably is that the water is going to melt the ice and then there will be some mix of water and ice left. Okay? Let's compute. Okay? What is Q1? Is somebody awake enough to say something at this point? What is Q1? Q1 is a heating up phase. So it's m, but now it's the mass of the ice. Okay, it's the mass of ice times the C of the ice times the final temperature of the ice minus the initial temperature of the ice. Okay, I've just expressed the formula, making everything explicit. The mass of the ice is how much? It's 1 kilogram. Easy. The C of the ice, well, maybe you think it's the same as the C of the water. Well, it's not. Okay? It's not. The C of the ice of the frozen water is about half the C of liquid water. Why that is, I don't know. Honestly, I don't know. And these are things which don't come from theory, but these numbers, they come from measurement. Okay? And sometimes these measurements are difficult. So there are specialists around the world doing this kind of measurements. So now we have the mass of the ice. We want the C of the ice. Where do I look for the C of the ice, in your opinion? Under what should I look? Ah, you know all that. Yeah, because I should look at water as a chemical substance. Okay, so in my list, I will look for water. In my French list, I will look for eau, of course. And here you have the chaleur massique, the specific heat. So if you look at water, which is this column here, this line here, what do you have? The water, when it is solid, when it is ice, it has a C of 2060. Okay? And when the water is liquid, it has a C which is different, which is 4180. Conclusion, it's about twice, almost exactly, twice as easy to warm up ice by 1 degree than to warm up water by 1 degree. Okay? So, that's the value you said. I don't know who spoke a few seconds ago. You said 2060, right? Yeah. Well, I have 2060 here in this table. Now you know sometimes these values vary. Sorry? In my course? In that table which I have added inside my course, there is this value. This table, you mean? Where? Oh, here, there's a second column. Yeah, ice 2000. Okay, so let's take that value. I mean, I'm not going to scream because you took 2100 instead of 2060, okay? Let's say 2100. So we have the same calculations. And then the fusion temperature of ice is 0 degrees, of course, minus the initial temperature of ice. Be very careful. You need to be careful with the signs, okay? It's final temperature minus initial temperature. The initial temperature is minus 10, and so here you have a plus, okay? Don't let yourself get fooled by this kind of things. So it's 2,100 times 10. It's 21,000 joules, okay? This is the energy needed by the ice, okay? Good, that's one thing. We know now 21,000 joules to go from here to here. The system needs to receive these 21,000 joules, okay? And who could give this energy? Well, of course, it's the water, okay? Because the water is warmer, the water is going to give energy to the lead, okay? Let's now compute how much energy the water is going to give. And of course, as we just discussed, the C of the water is twice as much as the C of the lead. So this is going to give us more energy than this is going to take. Okay, so let's compute now the Q for phase 3. The Q for phase 3 is the mass of the water times the C of the water times the final temperature of the water minus the initial temperature of the water. I've just rewritten the formula, okay? And the mass of the water, it's 1 kilogram again, okay? We have 1 kilogram of water, 1 kilogram of ice. Now the C of the water is 4,180. The final temperature of the water, be careful, now we are going down. So the final temperature of the water is 0 degrees and the initial temperature is 10 degrees. Okay? So this gives us minus 41,800 joules. Aha. How do you like the fact that we have a minus? Do you like that? Huh? You love it. Sorry? What did you say? It's exquisite. Oh, exquisite. God, the student says it's exquisite during my physics class. Okay, yeah, this is heat that is absorbed by the ice. Okay, this is heat we give to the system, so it's positive. This is heat which is released by the water when it cools down. Okay, so so we have this quantity here. Okay, so now what is the final temperature going to be? Well, you can imagine that, I mean, since both substances get to that point, then the equilibrium temperature is going to be 0 degrees, okay? Because the ice is going to melt because there is enough energy for the ice to melt. But then how much energy do we have left? Well, we have left 41,000 minus 21,000, and this energy which the water gives us in addition to the one that is needed to melt the ice, this quantity of energy will be melting some of the ice. Okay, let's do a drawing. Okay, the water releases 41,800 joules total. 41,800 joules. Okay, where do they go? Well, a part of it, and I'm going to write it here, a part of it, 21,000 joules, they go here to melt the ice. Okay, and so the rest is going, sorry, I said something wrong. This 21,000 come here to warm up the ice from minus 10 to 0. I said to melt the ice, it's wrong. And then the rest, so 41,800 minus 21,000, which is 20,800, the rest can be used to melt the ice here. Okay, do you understand? So we will say energy left to melt the ice is going to be Q3, okay, minus Q1. And now I need to be a bit careful. I need to not take the signs. So I need to take just 41,000 minus 21,000. So 41,800 minus 21,000. And that's 20,800 joules, which we have at our disposal to melt the ice. Okay? And so now, how much ice can we melt? Well, let's see. How much ice can we melt? Okay? Well, we have this 20,800 joules, which are left over from the water cooling down. Okay, this is our leftover. And this is equal to the mass of ice times the fusion latent heat. Okay, because this term corresponds to all the plateau here. Okay, but with 20,800, we can melt only a part. Okay, so now we need the latent heat of fusion of the ice. Okay, and then we will be able to compute the mass of ice which has been melted as 20,800 divided by LF. So let me look for LF. Okay, latent heat, latent heat, it's here. Latent heat for water. Fusion, it's 3.3 times 10 to the 5. It's 3.3 times 10 to the 5, so I add 4 zeros, okay? And this gives us something which is not very big. Something which is not very big is 20,800 20,800 divided by 330,000, okay? And that gives us 0.063 kilograms, which is about 63 grams. Okay, so we are actually melting only 63 grams out of this 1 kilo of ice, because this is what we can do with the energy we have left. I don't know if you followed the logics of this exercise. It's a bit, it's not like the others, let's say. Okay, so if I want now to do a summary of that, let me do a summary of that. Okay, let me do a summary and put in numbers. Again, I am going to do this diagram with the different values. But now I am going to consider the total energy needed for each phase. Here, for warming up our kilo of ice, this we know, we need 21,000 joules, okay, when we go up. Here, to go down from 10 degrees to 0, we get back 41,800. And here on this plateau, what is the energy we would need for to melt all the ice? Well, here the total energy will be given by MLF, okay, and MLF, let me just check. Yes, and MLF is now equal to 1 times 330,000, which is the LF of the water. So this phase requires, if you want to warm up to melt all the ice, it requires 330,000 joules, which is a lot. Okay? And what do we have? We have this guy, the water, giving us 41,800. 21,000 of which are going to be used by the ice for melting. So we have left here only 20,800 joules out of the 330,000 which would be needed to melt all the ice. This is why we can melt less than 10% of the ice. You see, we have less than 10% of this energy. We have 20,000, and so we can only melt 63 grams of ice. Okay? Are you convinced? Or are you sleeping? Ah, say something. They are here. They are here. They are here. Okay. You want me to explain again, or ça va, you got it? Huh? Ça va. Okay. Good. Okay, now let's do the next one, and let's be careful because as I noticed last time, when I wrote these exercises, I very stupidly confused the C's and the specific masses. So that's a bit stupid. So let me check that. Okay. Now you have a glass made of acrylic glass. Okay. So let's look for verre in this table. Verre acrylique. Voilà. That's the value I took here. I'm sorry, this was the specific mass. But now we need, I just want to check this number for acrylic glass. The specific heat is 1450. That's now correct. Okay, and for Pyrex glass, which is another type of glass, it's 830. This is correct. Okay, so the values are okay. Please correct that in your course. Okay, and be aware that sometimes I made a confusion, stupid confusion. Okay, so what do we have here? We have a glass which of mass 200 grams. So let's draw this glass. Okay, this glass has a mass of 0.2 kilograms, and it contains what else? It's a C of acrylic of 1450. Okay, and what else? This glass contains 200 grams. Okay, it's a glass of mass 200 grams, and it contains 2 deciliters of water, and 2 deciliters of water represents 0.2 kilos. So the same mass, but now this is the mass of the water, whereas this was the mass of the acrylic. The C of the water, we know it by heart. Okay, and then what else? The glass and the water are at a temperature of 20 degrees. So TIA is 20 degrees and TIW is 20 degrees. Okay? We put in this glass of water an ice cube of mass 20 grams at a temperature of -10. Oh God. Okay, so here we put an ice cube. Okay, this is ice. We put an ice cube inside, and this ice cube has what characteristics? The mass of ice is 20 grams? 0.02 kilos, and the initial temperature of the ice is -10 degrees. Okay, and the question is, what is the final temperature? Okay, let's see. Okay, we don't know exactly what the final temperature is going to be. We don't know now how much energy is available here. But one thing we can say is that probably this ice will all melt, okay? Because if we learn from the last exercise, we have here ice, 0 to 20 grams, and water, 200 grams, so the water is clearly taking over. We saw in the previous exercise that with 1 kilo and 1 kilo it doesn't work, but here it should work. Let's see. Let's do the calculations, okay? And let's do our diagram as usual, okay? So we have water at 20 degrees, okay? At, yes, 20 degrees, we have water. This is temperature as a function of time. And then together with that, we have ice at minus 10 degrees, okay? So here somewhere there's the 0 degree level, okay? And what is going to happen? The ice is going to warm up until 0, okay? And in doing that, it's going to need how much energy? Let's compute, okay? I'm progressing a bit cautiously because we don't know what the result is going to be. So let's try to figure out, let's compute this quantity of energy, okay? So this quantity of energy Q1 corresponds to heating up this ice, okay? It has to heat up from minus 10 to 0. So it's the mass of the ice times the C of the ice times the final temperature of the ice minus the initial temperature of the ice. What's the mass of the ice? It's 20 grams. So it's 0.02 kilos. What's the C of the ice? We remember it from before, it was 2100. Okay. And then the final temperature of the ice is going to be 0 minus the initial temperature of the ice. Be careful, like before, it's minus 10, so it's plus 10. Right? And so this is giving you a result which is 0.02 times 2100 times 10. Okay? This is giving us, and it's not much, 420 joules. Do you believe that? Yeah, I guess. 2100 times 10 times 0.02. Yeah, 420. Okay? That's the quantity of energy which is needed to melt the ice. Okay? And now we have other substances, okay? We have the water, which is on the other side. The water is at 20 degrees, and the water is going to cool down until where? We don't know, okay? So the other thing we need to know now, because we don't know what is the equilibrium temperature of the water, the other thing we need to know now is how much energy it takes for our ice cube to be completely melted. Okay? And obviously is going to be completely melted because there's 20 grams of ice cube and there's 200 grams of water. You know very well that when you put an ice cube inside a glass of water with 2 deciliters of water at 20 degrees, the ice cube melts. You know that, okay? So it's not forbidden to use some common sense in solving these exercises. Yeah? So how much does it take for the ice to melt completely? Well, it's the mass of the ice times the LF of the water, okay? The mass of the ice is 0.02 kilograms, And the LF, the latent heat of the water, of fusion of the water, is 330,000. Okay? So let's compute that. 330,000 times 0.02. That's 6,600 joules. Okay? As we saw in the previous exercise, it takes a lot of energy to melt ice or to freeze ice. Okay, much more than it takes to warm it up by a few degrees. Okay, so now we have Q1 plus Q2. How much is the energy which is necessary for the ice cubes to warm up? It's going to be 6,600 plus 4,020, and that's 7,020 joules. Okay? Good. And the water and the glass, now they will provide this energy which the ice uses. Okay, so the glass and the water, they are going to become colder by an amount equal to the energy that they are, by an amount proportional to the energy that they are giving to the ice. Okay, so the ice takes a total of 7,020 joules, while the water and the glass lose 7,030 joules, 7,020 joules. Okay, so now what we should compute is to what temperature we can go down if the water and the glass give 7,000 joules to the ice. Okay, so we need to compute that. We need to say 7,020 is equal to what? So we have two terms. We have the water and we have the glass. Okay, let's say the mass of the water, the C of the water, the final temperature of the water, minus the initial temperature of the water. This we know it's 20. Okay, this is the energy which is going to be given by the water. But the glass is also giving us energy. So we have the mass of acrylic times the C of acrylic times the final temperature of acrylic minus 20, which is the initial temperature of acrylic. Okay, I'm computing now what final temperature will give us this amount of energy if we remove this amount of energy from the water and the glass. What's the final temperature going to be? And of course, the final temperature of the water and the final temperature of the glass, they are going to be the same because the glass and the water are in equilibrium. So I'm just going to remove this suffix I had put there. And now we are going to try to determine the final temperature. Okay, and all the other things we know. Okay, so we know the mass of the water, which is 0.2. We know the C of the water, 4,180 times TF minus 20. We know the mass of the glass. The mass of the glass was 0.2. We know the C of the acrylic is 1,450. And then TF minus 20. And this should be equal to 7,020. Okay. Are you following? Ça va? Yeah, ça va. Ça va. Good. Okay. So now, how do we solve this thing? Well, we have to write that 7,020 is equal to 0.2 times 4,180 times TF minus 0.2 times 4,180 times 20. Okay, I'm just distributing this. And then we have plus 0.2 times 1,450 times TF minus 0.2 times 1,450 times 20. Okay, so these two terms here which are numeric. We will throw them to the other side, and then we will have TF multiplied by these two guys. So it's going to be TF times 0.2 times 4,180 plus 0.2 times 1,450. This should be equal to all these guys together, 7,020 plus, because I'm going to the other side, so the change signs, the sign change, sorry, 0.2 times 4,180 times 20 plus 0.2 times 1,420, 450 times 20. Okay, and then the final TF will be just this divided by the parentheses. So I'm going to write it here. TF is going to be 7,020 plus 0.2 times 4,180 times 20 plus 0.2 times 1,450 times 20 divided by 0.2 times 4,180 plus 0.2 times 1,450. Oh, sorry. Yeah, excuse me. Okay. And now we need to compute this guy. So let me compute. 7,020 plus 7,020 plus bracket 0.2 times 4,180 times 20 plus 0.2 times 1,450 times 20 bracket equal. This gives me 29,540. Is that correct? Yeah, sounds correct. And this is divided by 0.2 times 4,180 plus 0.2 times 1,450. No, I made a mistake, sorry. 0.2 times 4,180 plus parenthèse 0.2 times 1,450 parenthèse égale, it's divided by 1,126. Wow, it's going to be badly wrong. And now if I do 29,540 minus 1,126, I get 28.4. Where am I doing minus? I did that. It was to see whether you are awake. 0.2 times 4,180 equals 836. I did minus. No, plus. Wait. Yeah. It's not. Are you sure? 29. I will check on the video. 29,540 divided by 1,126. It's, yeah, it's 26. Well, it doesn't change the fact that it's wrong. Okay, it's 26.23 degrees. What do you think of this result? Is it correct? No, it's wrong. It's clearly wrong. Okay, so what's the reason here why all this is wrong? I don't even know myself. I have to think a bit, because last time I did it, it went well. What is the problem? What is the problem? We have Wait, where's the beginning of the calculation? It was here. Do you have any idea about what I did wrong? No, I don't. I have to think. Here, tell me. Where? Where do you mean that? Where is it? Yeah. No. Here? No, no, it's not a minus because this is now, you see, it's minus when it's on this side. So when I put it on the other side, it becomes plus. Okay. But now the question maybe is a question of signs. Because here, maybe I should put here minus and here minus, okay? Because these are energies that the system is giving us. So these energies, these two energies, they should be negative, okay? Indeed, you see these two terms, they must be negative. Why? Because the final temperature of the water, we expect it to be lower than the initial temperature of the water, which is 20. Okay? The final temperature is going to be maybe, let's say 15. So if I have 15 minus 20, this term here is going to be negative. And this term here is going to be negative too. So in that case, I think this is the answer. I hope I should take the minus, the opposite of this quantity 7020. This quantity is counted positively when the ice receives it, but you have to count it negatively when the water is giving this quantity of heat. Let us try. Let us try. Okay. And in that case, if I change the sign here, but I didn't end up on that problem last time I did this exercise. Whatever. So here it's minus, and so here it's minus, and so here it's minus. Okay? And now let's see. Of course, it's going to change. It's going to, of course, decrease the temperature. But let's see now by how much. If I do now 0.2 times 4,180 times 20 plus bracket 0.2 times 1,450 times 20. This is 22,750 minus 7,020. This gives me, it gives me half. So this is much, much, much better. And so now it's 15,500, okay? And so the final temperature is going to be something like 14 degrees. 15,500 divided by 1,126, that's 13.76 degrees approximately. Okay, and that's much better. Okay, that's much better. We have an ice cube, we put it inside a glass with 2 deciliters of water at 20 degrees. The ice cube melts, it sucks energy from the system, and thereby reduces the temperature. So the previous result was completely wrong. This one sounds correct to me. I don't know why I don't know how I did this problem the other times without ending up on that situation. But I think this is correct. I mean, this has to be negative. Okay? Voila. Okay. So, So we are done with the course, with the part of the course that I printed. Now, what we can do is we can continue this a bit because there is, who is doing all this noise? Yeah, because there is a secret part of the course which I didn't give you yet, and I will give it to you for today and next week, okay? This chapter about heat transfer and heat equilibrium is over. There is another chapter. There is still a bit in that chapter that should be studied. I will give you the course. I will put it on Classroom in a moment. But today I will do the course like that based on my own neurons. And one thing I would like to tell you is about heat transfer. Okay, this is something which is important, and this is something quite easy to understand. There are no equations, nothing, but it's useful in your. It will be in the course which I will give you. Okay, but you can take notes if you want. Okay, the question is, how does heat transfer from one substance to another? So we will study this, and then there will be a small section which we will do next week about dilations, etc., as an effect of temperature. Heat transfer. Okay, let's imagine you have, Ali, this is a room which I am drawing with an impressive sense of perspective. Okay, this is your bedroom, and under your bedroom, under your window, which is not big because you've been a bad girl, and so you're locked in there. Under your window there is a radiator, and here also there is another radiator, so I can do multiple drawings. Okay, so this is your bedroom, with two radiators, let's admit. Okay, and this is your bed here. How the hell does the heat which is brought into your apartment by the radiators arrive to your heat, to your bed? Can you answer that question? Okay, here the radiator is a source of heat, and the question is, how does this radiator heat up the whole room so that even your bed is warm? What would you say to that? Do you have an idea? It heats the air, and then what? Yeah. Yes, but there's one phenomenon you are missing. If you heat up air, what happens with this air? Does it become more dense or less dense? If you heat up air, more dense, okay? Imagine this, imagine that this is cold air, okay? What happens if you warm it up? The molecules are going to vibrate more, they are going to undergo more shocks. So actually, warm air takes less space than cold air. Warm air is lighter. This is something I'm sure you know. If you take these warm air balloons, you know these balloons people like to travel with, and these balloons, they are filled with warm air. There is here a burner and a flame which heats up the air. Why is this thing flying? This thing is flying because the warm air which is here is more light than the air which is around. Okay, so if you warm up a substance, it decreases its specific mass. You understand what I mean? Especially a gas. If you warm up a gas, it's the distance between the atoms slightly increases and the specific mass decreases. Okay, so what happens to this air which has been warmed up by your radiators here, if it's lighter, what happens to it? The others can answer too, it's allowed. What the hell happens to air which is heated up by your radiator? Because if the air remains here where the radiator here is, it's not gonna heat up your bedroom. Okay? No idea? Well, this air is going to be lighter, and what is lighter than the rest goes up. Okay? Warm air goes up. So this warm air is going to go up along the walls, and as it touches the walls, it will lose temperature, and it will end up everywhere in the bedroom. Okay, this air is going to do things like that in the bedroom. And similar here, okay, the warm air which is heated up by this radiator is going to go up, and then it's going to come down, and then when it's cold, it's going to come back and be heated again. Okay? This is why if you look at your place, unless your place has been repainted recently, if you look at your place, you will see traces of dirt on the wall, close to the edge, on top of radiators. Okay, it's always like that. It's difficult to avoid. And why is that? It's because all this air which is circulating during the winter when the heating works, all this air, it passes here, and here it turns, and sometimes it's full of dust, and this dust gets attached to the wall. Okay, that's why your walls are dirty on top of radiators. Okay, so this kind of movement, this way of transmitting here heat, it has a name. Do you know the name by any chance? This phenomenon is known as convection. Okay, convection, we will talk about others in a moment, but this is one mechanism in which heat can be transferred inside a liquid or a gas. This works only inside liquids or gases because they need to be able to move. You cannot do that in a solid. There are other phenomena in solids. Okay? But I can give you another example, which is again a home example. Okay? Let's assume you are warming up water. Okay, you have your pan. Inside your pan, you put your water here. And you turn on the heating. You turn on the stove. Okay? So what is going to happen if you turn on the stove? Well, the bottom of the pan is going to become very warm. It's going to become much warmer than 100 degrees, by the way. Okay, so it's going to transmit heat to the water, but the water is not going to go higher than 100 degrees because water boils at 100 degrees. But what happens in here? Well, the water which is here on the bottom, it gets heated up by contact with the bottom of the pan, and so it's going to become lighter. It's going to have a lower specific mass than the cold water. Okay? And so this water which has been heated up, it comes up. And when it comes up, it cannot go further. So it goes to the sides and then it comes back. Okay? And so in a pan of water which is heating up, you have this structure. Actually, if you look at it from above, okay, it's a structure. I don't know if you understand what I want to say. It's going like this. So from the center, the water is coming up, then it's going to the sides, going down, getting colder, touching again the bottom of the pan, and then it's coming up again. Okay, this stuff in French we call it rouleau de Bénard. I like that, and I say it all the time. It's not something very famous. Okay, but it's rouleau de Bénard. So again, in a liquid, heat is transferred by convection. That's one of the main phenomena which accounts for heat transfer. So convection. Okay, convection is the big heat transfer mechanism in gases and solids. For instance, I can give you another example about convection. Let's assume you have a window. Okay, you have a window, and the window is a nice window. It's isolated. It has two layers of glass, and in between that there is air. Okay, well, what happens if one window, one glass, the one which is outside is cold, and the glass which is inside is warm? What's going to happen? Well, it's pretty obvious. The air which is close to the warm glass is going to become lighter and is going to come up. And then on the other side, now it comes up, it touches the cold window, and it becomes cold, and it goes down. And then when it's down, it goes up again. Okay, so the circulation of air transfer a lot of heat from the warm window to the cold window. Okay, and this kind of convection movements we cannot avoid. Okay, we could avoid that by putting some foam here. Okay, but if we put foam inside the window, you won't see through the window. Okay, so convection is one of the main phenomena which makes you lose heat, etc., etc. That's just one of the mechanisms. There are two more. Do you know the other ones? Have you ever heard of that? There is one which is pretty obvious, is conduction. So conduction works in solids, whereas convection, as I said, works in gases and in liquids. Okay? Conduction works in solids. What's conduction? You have a piece of well, let me not put it here. You have a piece of metal, let's say. You put one flame at a certain end. This end warms up, and then the heat is transferred through the bar of metal. Okay, so progressively the heat is transferred to this bar and arrives to the other side, and there are equations which tells you at which velocity, etc. it works, and the transfer velocity is different for different substances. Copper is one of the best heat transmitters. Okay, and how does that work? That's a completely different mechanism from the mechanism of conduction. This is because if you heat up this part of the thing, of the bar, your molecules, they are going to get more active kinetically. Okay, they are going to vibrate more around their stable position. And this vibration is going to affect the molecules which are next to them. So little by little, through the material, this thermal agitation is going to be transmitted from each atom to the next atom, from each molecule to the next molecule, until the heat arrives on the other side. Okay, this is conduction. And this is exactly what happens in your pan under the boiling water. Okay, the bottom of the pan is made of metal. Metals are good at conducting heat. So here you have a source of heat which is becoming warm, your stove, and the bottom of the pan is conducting the heat to the water, which is then heated up and has these convection phenomena which allow the heat to be distributed inside the water uniformly. Okay? So, convection, conduction, there is a third one. Have you heard of it? Think about the sun. You lie in the sun, you feel warm. Why? I'm sorry to ask very basic questions, but why the hell do you get warmed up by the sun? It's not convection because there is no gases or liquid between the sun and us. It's not conduction because there are no solids between the sun and us. So how could the heat of the sun be transmitted to us? What do you think? Hmm? Reflection. Well, yeah, reflection, but why do you want it to reflect on? There is nothing between the sun and us to reflect the heat. Okay, let me do an experiment for you guys. Okay, this is my hand. This is a lighter. I do feel the inside of my left hand. I do feel warm. Why? Okay, it's not the flame which is making the gas go up or whatever because it's coming up straight towards the camera. What is conducting heat from here to my hand? Huh? Well, if you don't know it, I will tell you. Huh? No, no, there is no air between us and the sun. The last mechanism is radiation, rayonnement in French. Okay, when you have a source of light, or more generally, a source of electromagnetic radiation, this radiation is emitted, can travel through empty space. This is what happens with the radiation from the sun, okay? And the radiation that the sun emits contains light, of course, visible light, blue, red, green, yellow, etc. But it also contains another type of rays which are called infrared rays. Infrared, they have an energy just below the energy of light. Okay, it's infrared because it's below the red color. And these rays, they can heat up. You know very well in the cafeteria, they have infrared bulbs over the food to keep it warm. Okay, and then there is UV, ultraviolet, and then there are many other things. Okay, but this radiation, which is emitted by the sun, and that you can see like a flow of particles, which we call photons, light it as a wave, but you can also see it as a flux of very, very, very tiny massless particles which carry energy, which are called photons. Okay, you can see that as this flux of particles, and these particles, they are traveling from the sun towards us. Okay, and in this way they are transferring heat to us. By the way, when I did the first drawing with the radiator, I was missing something. Now that we know better, okay, on that picture I can add the fact that the radiators, they radiate. Yeah, that's why they're called radiators. Okay, they heat up the air here and make it turn and heat up by convection. But they also radiate. This is the reason why they are called radiateurs. Okay? This is because they radiate. And why are they usually white? They're always white, the radiators. Did you notice? Why the hell are they white? Huh? I'm asking you terrible questions in the morning. No idea? Exactly. White radiates much better than black. Okay, so the brighter an object is, the more it's going to radiate energy. If you take a white car and you park it in the sun in the summer, and next to that you park a black car, same model, okay, same characteristics, you will see that inside the white car it will be much less warm, because the white color, first of all, is reflecting the radiation from the sun. And second, it's emitting more. So if it's emitting more heat, it will be more cold. Okay, and a black car, it absorbs more radiation and it emits less. So inside a black car, after you park it in the sun in the summer, very fast you regret your choice of the black color for the car. Okay, so there are all these mechanisms which allow heat to be transferred. It's not going to get more complicated than that with equations. Of course, you can write equations for all that. Convection is difficult to modelize with equations. Conduction, yes, you can modelize it with transport equations, but this is not high school level physics. Radiation, you can also modelize it pretty well as waves or particles. Okay, and these three mechanisms, they always work together. Okay, let's say now I give you a final example, and then I let you go back to your families. Okay, imagine you have here a dish of food, and the dish is very warm. Your mother has just, or your father, let's be modern, has just brought some nice food to you. It's very, very warm, okay? And you are here, uh, you are here. Oh, it's not so bad. It's not so bad. Oh, yes. So who does this look like in the class? Hmm? You really don't want to talk. Okay, you are here, and you are looking at this plate, okay? And you feel a bit of heat on your face. So what mechanisms are working here to make you feel the heat of the plate on your face, okay? There are two mechanisms acting in this situation. Can you tell me which two? Out of the three we mentioned, convection, conduction. Sorry? Yes, not only vapor. Yeah, vapor, of course, vapor is coming up and vapor is warm, okay? But you have also air, ambient air. The ambient air, which is cold, is going to come in contact with the food here, which is warm, is going to get warmed up, and it's going to go up. Okay, and of course, what goes up at some point must come down. So after some time, the air, when it loses its heat, it comes down again and starts again this circle. Okay, so we have, of course, convection, which is agitating the air and transmitting heat. One part of the heat here comes from convection, but not only. Okay, there is another mechanism, which is radiation. This dish is warm, let's say it's 80 degrees, and so it's radiating heat in all directions in the form of electromagnetic radiation, and this radiation arrives to your face and it heats up your face. Okay, there is no conduction here because we have no solids between our face and the dish. There is conduction inside the dish because the food is inside the dish and it's warming up the dish. So inside the dish you have conduction, okay, which is heating up the dish itself. Okay, so that was an example to illustrate these three transfer mechanisms. And these things can be useful for you if one day you have a house and you have problems heating the house. Then you can, if you understand this, you're going to be better off fighting your losses of heat. Okay, voila. I will let you go. Next time we are going to do dilatations, etc. We're going to finish nicely the program of the year. So next year If you didn't sleep too much during these classes, next year you will have everything you need. We did the program. Okay? Okay. So have a good day, be good boys and girls, and see you next week. Okay. Bye bye. Bye bye. Bye bye. Bye.